topic of this lecture is marginal treatment effects. In undergrad and master's courses, you may have heard about difference in difference estimates or estimators, regression discontinuity, and especially instrumental variables. But not so many students have heard of marginal treatment effects. However, marginal treatment effects are very, very important because they are what underlies at least two if not three important techniques of causal inference. So they are critical to understand randomized experiments. They are critical to understand instrumental variable estimates, and they're also critical to understand regression discontinuity. Therefore, let's dive into that. So the point of departure of why we're talking about this topic and trying to get a deeper understanding of how treatment effects work is that in the past lecture we have seen that instrumental variables estimators that are commonly used identify a local average treatment effect. So the estimates that we're getting are not informative for the whole population that we're interested in studying and from which we have drawn a random sample, but they're only informative about those people who comply with the instrument, as in whose behavior is changed by the instrument. And whether that is an interesting population to study or not depends on the context, depends on the question we would like to answer. In some cases it is, in many cases it is not. And so therefore we need to think carefully about what lies beyond or what lies behind a local average treatment effect, and how can we generalize from the effects that we're getting when using, for example, an instrumental variable estimator, or when running an experiment, how can we generalize to other parts of the population? So what this lecture will use a lot is we will talk a lot about target parameters. Target parameters are those that we are actually interested in. So suppose you work as a consultant or you work for a research institute and you want to understand what is the effect of a given policy on a given population of interest. Well, that's the target parameter. I don't know, you have you offer free childcare to parents and you want to know to what extent that affects female labor supply. Then you must have some population in mind that you actually want to know, for which you actually want to know whether that policy is effective and how big that effect is. The problem is that a local average treatment effect that is identified through an instrumental variable approach may not coincide with that target parameter. And we will later learn about other types of parameters that potentially are close to those target parameters, and that may also, and that may be more important to know about than the local average treatment effect. So they are listed here, but we will revisit them a little bit later in the lecture in a future video. But let's start here with the basic setup. So we have again the treatment effect setup where we have a group where we have people who are treated and other people who have not been treated. So we have a binary treatment. That can either be an experimental treatment, but it can also be something that units have chosen. And so we then have to distinguish again between potential outcomes. So these are the outcomes for people in case they are or are not treated. So that's the potential outcome if a person is treated, and that's the potential outcome if a person is not treated. So take again the example of free childcare. then the potential outcome Y1 would be a woman's labor supply if the family received free childcare, and Y0 would be a woman's labor supply if the family did not receive free childcare. And we have the fundamental problem of causal inference that we only observe each unit in one of the two states, but never in both at the same time. And in some so at some point in this lecture, we will also then talk about instruments, which we see here as a force that affects the likelihood of choosing the treatment. And so if you think about treatment as a deliberate choice, so you choose whether to actually send your child to childcare or not, then the instrument could be a cost shifter. The example here is that child, you get a voucher that allows you to send your child to childcare for free. And then that would change the cost of choosing to get treated, as in to actually send your child to childcare. Now, the framework for studying, for looking into marginal treatment effects is the so-called Roy model. What the Roy model tells us simply is that for each person, the potential outcomes have a component that is common to everyone in the sample, or to everyone, in fact, in the population, and a component that is idiosyncratic. So for those people who have been treated, they have some determinants that are common to everyone who's been treated and that are typically also observed. But there are also some idiosyncratic determinants. And the same goes then for those units who are not treated. Okay, so the example again is that you may observe that people who send their kids to childcare may be younger than those who don't, or maybe more educated than those who don't, or less. That would be the difference between mu1 and mu0. But then there are also factors in that, let's say there may also dimensions that we cannot observe, but along which families who send and don't send their children to childcare may differ along those dimensions. And so when we then think about the individual treatment effects, which is what we see here, so that's the individual treatment effect. That treatment effect then again has a component that is common to everyone, and an idiosyncratic component that depends on that differs by individual. And so what that means is that the likelihood of actually choosing to get treated may differ between people or units. Why? Because the benefits from getting the treatment differ across units. And so the idea here is that on average, these idiosyncratic terms are zero, but for some people, this difference here, the difference of those two terms, is highly positive, and so they have a huge gain from getting treated, and others may have a very low or gain, or may even be at a loss. And so across the population, the treatment effects are not homogeneous. That's the most general framework that we're going to look at. And now what we do is this is probably the closest the causal inference world is getting to actual microtheory. Is what we want to do here is we want to actually model the selection into treatment. Okay, so we want to express the likelihood or the fact that someone takes the treatment or not as a function of an instrument and, again, an idiosyncratic component. Now, the simplest possible way to do this is to just consider a person's latent net benefit of choosing the treatment, which is that you have a common gain from choosing the treatment. You have an instrument, and you have then also, if you take the negative of that, a cost of choosing the treatment, or what's also called resistance to treatment. And again, that may vary across people in the population. And so some people may have a very low cost of participating in a program, whereas for other people this cost may be very high, either because of their preferences, or because of the social stigma attached to it, or because the opportunity cost of their time is very high, something like that. Now, obviously, you can augment this equation by adding additional determinants of the treatment choice that are observable. That will not change anything of the essence. Okay? But what we have here is basically this equation per se is not observable for us. What we observe rather is whether the person actually has chosen the treatment or whether they have not chosen the treatment. And what we also observe is the state of the instrument. Okay, so this is basically a theory of the choice of the selection into treatment. So the idea is that if the gains from choosing the treatment are higher than the costs, the person will choose the treatment and otherwise not. Okay, so it's basically a revealed preference approach, or follows from a revealed preference theory, whereby if we see that someone has chosen the treatment, it must mean that the gains for that person must have been higher than the costs. And if someone has not chosen the treatment, then the costs must have been higher than the gains. That's the very basic idea. That, of course, does not include too many behavioral insights and so on. But that for these type of models is also would also be a little bit beyond the point. And now let's take all these ingredients of the model. So this equation that we see up here is often called the participation equation. So that determines whether someone participates in a program or not. And we know that how the potential outcomes depend on individual as well as idiosyncratic factors. Now let's bring them all together into a regression framework. And so what we have basically is, what we would regress is, we would regress the outcome here on a dummy of whether the person has been treated or not. Right? That would be the very basic regression. Okay? But here, notice that we still allow the treatment effect, the individual treatment effect, to vary across people. However, if we only observe for each person one treatment status and one outcome, we cannot identify this parameter. Okay? Because we would need to have at least 2 observations for each person to back this out for each person. So what we do instead is to say, we want to know what the average treatment effect is, at least in this case. And so we basically, instead of having a treatment effect that varies by individual, we want to at least get at, what is the average treatment effect if some people are treated and others have not been. That's what that equation at the bottom gives us. And how we get there is by, first of all, looking at the individual treatment effect. Now remember that each of those terms here has a mean of 0, yeah? Such that the difference between those common components of the treatment effect that are common to all individuals, well, that's actually the average treatment effect. Okay, so that's the treatment effect that is common across all people, and the rest varies across people but is mean 0. And so now if we take this equation here, or this, and plug it into the equation up here, we arrive at, let's just call this for a second, equation 3. We arrive at that, and that gives us a regression equation. Okay? So what we have here is we have an actual regression equation that would allow us to back out the average treatment effect. Okay? So across all the people in my population, if I give these people the treatment, then the average gain in terms of outcome is this expectation here. But you notice already that there is lots of components that enter the error term in a regression. And we will learn in the next couple of slides what these components are and why they are so important. And this is what we see here. Okay? So the big problem here is that if you look at this equation, equation 3, the first line is that the regressor of interest is D, but that regressor also appears in the error term. So naturally, you have the situation that the covariance between the treatment and the error term is different from 0. And therefore, we have an heterogeneity problem, and therefore our estimate of the average treatment effect will be biased. Let's take a closer look at the selection bias here. So we have seen on the previous slide that the treatment is the regressor of interest, but it's also part of the error term, and therefore that covariance here does not equal 0. And we can even disentangle that because we have a binary treatment, so we can write this this expectation as follows. So that covariance basically is the product of the likelihood of getting treated, or in that case the share of units that get treated, times the expected idiosyncratic outcome, right, of those who get treated. Right? And so obviously, if those people who select into treatment are systematically different from those who do not, then that will be different from 0. As soon as you have some people who get treated, and as soon as these people differ systematically, you have that covariance that differs from 0. And we can even look closer at the selection bias, either by running that regression that I've shown on the previous slide, or by just comparing the outcomes of people who chose to get treated and those who did not choose to get treated. Running that regression or doing that comparison is the two things are equivalent, okay, because we have a binary treatment here. So what that gives us is we can rewrite that difference as the true average treatment effect plus a selection bias. And that selection bias, again, is the difference in the idiosyncratic outcomes of those groups that get treated and those groups who did not get treated. So here are the interpretations of those two terms. So this is the first expectation is the unobservable outcomes of the treated in case of treatment. And then we also have here the unobservable outcome of the untreated in case of no treatment. Obviously, what we don't have here is the counterfactuals, which is, what would be the unobservable outcome of the treated in case of no treatment and vice versa for the untreated group. So if you do a naive comparison of those who chose to get treated and those who didn't, what you get is the true effect plus a selection bias. That's the important insight here. And now we can think about, well, how can we eliminate this selection bias? So to eliminate it, those two expectations have to be the same. They have to be 0. Or that the one minus the other has to be 0 or both together 0. Now you get this under two conditions. So one is that if the treatment was randomly assigned, right? Because then in expectation, the potential outcomes of those people who were treated and those who didn't should not differ. And that's why experiments are so powerful and are considered so credible. But there is another element here to it, which is that the compliance with the assignment has to be 100%. Right? So if people do not get to choose who takes the treatment and who doesn't, but they're forced to take the treatment if offered the treatment, then those two expectations are the same. However, if we're in a scenario like you have in most randomized experiments in economics and psychology, where people get treated or are assigned to a treatment group, but whether they take the treatment is then up to themselves, then those two expectations may not be the same. That's very, very important. Okay, so you may not be able to estimate the average treatment effect simply because some people, when offered the treatment, choose to get treated and others don't. And so therefore, we can already learn a little bit, or a good bit actually, about estimation of causal parameters and what some of the problems can be. So obviously, if you have selection into treatment, so if it's under people's control whether to select into treatment or not, consistently estimating the average treatment effect is not possible. So what are the implications of that? Now, when you have a randomized experiment and you randomly assign a variable z that is basically an instrument, such as a voucher that then allows you to get treated, if compliance is perfect, you have no selection bias. With imperfect compliance, it's not really a selection bias. People don't refer to it like that because it's not that people could select, that subjects could select into the instrument. The instrument was randomly assigned, and then those who received the invitation to get treated, those who received, for example, a voucher, then choose or do not choose to get treated. So what we would get from a randomized experiment with imperfect compliance is still a causal effect, but it's not the average treatment effect. It's something else. It's a local average treatment effect, or depending on what estimator we're really using. In observational studies where you don't have a randomization of an instrument or of the treatment itself, you have an omitted variable bias. So the selection bias is an omitted variable bias. And you have this double whammy because on the one hand, you because first of all, you cannot credibly argue why this effect is causal due to the selection bias, and you even if it was causal, then you would still not be able to estimate easily the average treatment effect. Now, whether the average treatment effect is such an interesting parameter in itself, we'll see in a later video. Yeah, but for the moment, let's assume it's the treatment effect that is of the average person in the population. It's probably also not such a bad parameter to look at least to start with.